Good morning, everyone. Welcome to week 10 of our biochem reviews. We are nearing the end of this semester. I know your exam is next week, so next week I'll do my best to plan a little bit of a unit review as well as the content for the week. So this is really where we start doing real biochem. We have our glycolysis, gluconeogenesis, glycogenolysis, the Tca cycle, and electron transport chain from now until the end of the semester. These are some of the major topics that you'll be dealing with. And these are really what are significant about biochem and one of the biggest reasons we take it. So I'd like to, and I went over glycolysis very briefly last week, but I want to do it again, and then we can start talking about the regulation. We can talk about the energy. We can talk about all those things that are also incredibly important. I want to just very briefly go over it because I want to make sure we all have a very good background on the reactions before we start. So our first reaction is kind of one of the easiest ones. It is glucose, D-glucose from our carbohydrate unit, though not vitally important, being phosphorylated by hexokinase, basically everywhere except the liver where glucokinase is. And so this has obviously ATP as one of the things we use and has magnesium as a cofactor. In other words, magnesium helps speed up this reaction. Most of the time when you have these metal ions based on our, I think it was the end of unit 2 when we were talking about the mechanisms of enzyme catalysis. Metal ion is really good for stabilizing a negative charge, right? So one of the things that I talked about last week that I'd like to really make sure that I emphasize again is the idea of energy. So the delta G of this thing, we know that the delta G of ATP hydrolysis is somewhere around -30. So even if this first thing is the phosphorylation of glucose to D-glucose is non-spontaneous, it's going to be driven forward by this very spontaneous process and give you a delta G that's fairly negative. I believe the number ends up being somewhere around -18 or -19. To be honest, it might have been 16. I do admit I might have those mixed up. So the point is, this is a very, very energetically favorable reaction for us. And this is one of the things that drives glycolysis, called the priming reaction, because it prepares us to make use of the energy that we have to make more effectively. Okay. The second reaction is an isomerase reaction. And why we need this isomerase reaction comes down to kind of like 3 steps from now. So we have to remember that this process is all together. So we can look at a reaction and say, well, that doesn't make sense. That's not very favorable. But the reaction itself is a great way for the next reaction to happen, right? So when we shift to fructose, we can, well, let's see, what's the biggest difference? Carbon number 1 is here. Carbon number 1 is here in fructose, okay? Phosphofructokinase, or PFK, or PFK1, if we want to be more specific, we can easily phosphorylate carbon number 1, whereas it's a little bit harder with glucose. So these two reactions are kind of working together to help us out, okay? I'd also point out an isomerase reaction doesn't take a ton of energy, right? We're just kind of shifting things a little bit. Yes, a 6-member ring is a little bit more stable than a 5-member ring, so that could play a role and make this a little bit non-spontaneous. But we're not adding a reactant. We're not hydrolyzing ATP, which releases a ton of energy. This is fairly neutral in terms of spontaneity, which means that it can be driven by concentration and it can be driven by the reactions before and after of spontaneity. So because we know this first reaction is very, very spontaneous, because we're using ATP hydrolysis, we get a buildup of glucose 6-phosphate. Glucose 6-phosphate then shifts the equilibrium. So now we're significantly to the left of K based on Le Chatelier's principle. So to compensate, this reaction is going to happen a lot quicker. Okay? It's all about these concentrations and these energy values. This next reaction is also going to be pretty spontaneous because, because we're using ATP hydrolysis once again. Okay? And this number is in erythrocytes or in blood cells. It's also about a delta G of -19. And this is all kilojoules per mole. I'm just looking that out for convenience. Once again, we see that magnesium cofactor. Once again, stabilizing that negative charge. Okay? Very spontaneous reaction. Okay? The next reaction is the cleavage. And this is one of those reactions that I think a lot of people can get a little bit confused. So this is one benefit to having fructose is we can basically cleave this thing right down the middle. Okay? Between carbons 3 and 4. So just for convenience, this is 1, this is 2, 3, 4, 5, and 6. So we're just going to cleave between carbons 3 and 4 to get 2 3-carbon monophosphate products, G3P, or glyceraldehyde 3-phosphate, and DHAP, dihydroxyacetone phosphate. Okay. We want G3P. That is our ultimate goal. So to get that, the fifth step is called Triose phosphate isomerase. Very simple reaction. All it does is convert DHAP to G3P. And so that's why on the second half of glycolysis, you just see 2, 2, 2, 2, 2, and so on, because we have 2 G3P coming from 1 glucose. Okay? So the thing that I also want to point out is we have phase 1 and phase 2, but what do these mean? Okay? Phase 1 is all about priming. It's getting us ready. Okay? Phase 2 is giving us energy in the form of ATP and NADH and converting what we have to pyruvate so we can get a ton more energy later on. Okay? So this reaction, or I should say the next reaction, the first reaction of phase 2 is the conversion of G3P to 1,3-bisphosphoglycerate. So I want to point out that this is a phosphorylation reaction. Okay? We're not using ATP. Okay? Why is this important? It's important because the fact we're not using ATP tells us a lot. Okay? It tells us that this thing is using NAD plus to NADH as the driver of this reaction. And it's also telling us we're not going to have a number like this -18, -19 that we saw in phase 1, because ATP hydrolysis is a really, really spontaneous one. Okay? So despite this one changing the phosphorylation, it's not going to be as, should I say crazy, as the other reactions that we've been dealing with. Now we look at reaction 7. Reaction 7 forms ATP. Okay? This formation of ATP uses our 1,3-bisphosphoglycerate, so a diphosphorylated product. It once again uses magnesium to once again stabilize that negative charge. It's never going away, and form some ATP. So at this point, if we stopped right here, oops, I apologize, I didn't mean to cut that off. There we go. If we stopped right here, we've used 2 ATP on the left side. We've gotten out 2 ATP and 2 NADH. As of this point, glycolysis is energy neutral. Okay? And actually a little bit more than neutral because we do have reducing power in the form of NADH. Okay? But glycolysis can keep going. So everything after this is a plus for us. Okay? So the next reaction, reaction 8, is catalyzed by phosphoglycerate mutase. Mutase is fairly similar to an isomerase. I know there is one detail that set them apart. I'm afraid I don't remember. And it moves our phosphate group. The one thing I want to point out is, once again, with our phosphate group, we have a magnesium. These guys are best friends. Okay, they never go away. All right. Finally, reaction 9 is called enolase. So if you guys think back to what was it? Organic chemistry 1, I believe it was. The keto-enol tautomerism. This is an enol. It's a double bond and an oxygen, both attached to the same carbon. Okay? This is relatively unstable. And I say relatively because we favor the keto form over the enol form, because the keto form is more stable. So this enolase is a dehydration, as you can see with this, or a condensation reaction. Both are acceptable terms. And what it does for us is it sets us up for reaction 10, where we want to get rid of this unstable enol. And so we grab some ATP and once again, magnesium never goes away. And then we get pyruvate. And I like to think of pyruvate as more energy potential. It isn't actually energy, it's not reducing power, it's not anything like that, but it gives us the chance to make energy at some point. So when pyruvate can hopefully eventually enter the mitochondria and participate in the Tca cycle or the citric acid cycle, the whatever you want to call it, the Krebs cycle, gives us a ton more energy. So that's glycolysis in a nutshell. So which reactions are irreversible? Okay, in other words, if a reaction is somewhere around, I don't want to give a number because I'm not actually certain what the number is. It changes depending on the situation. But if you have a delta G value that's relatively close to 0, so either positive or negative, that reaction can be reversible. Like I said with reaction 2, it's fairly neutral in terms of delta G, meaning it's mostly going to be driven by concentration. Okay? And that's why this graph over here, I cut it off because this shows the quote-unquote 11th reaction, which is the reaction of pyruvate into lactate under anaerobic conditions. We'll talk about that later today. These are just the first 10 reactions and just the essentials of glycolysis. And if you guys notice, reaction 1, very spontaneous. Reaction 3, also very spontaneous. And reaction 10 is very spontaneous. Okay, every other reaction is close to 0. So under the right conditions, they can flip-flop, okay, and they can be done in a reverse reaction, okay? So I want to pause and highlight this for 2 reasons, okay? The first is that steps 1, 3, and 10, these are the steps that we need to regulate, right? Every other step, I mean, it can happen, but it's not going to cost us much energy, and it can just happen in reverse pretty easily. But if I go through step 1, if I go through step 3, if I go through step 10, that's a lot of energy. It's a lot of energy that I have to deal with. Okay? I don't want to have to. So what can I do instead is regulate reaction 1, regulate reaction 3, regulate reaction 10. And once I've done that, I no longer have to worry about these really high energy reactions. Another thing that I want to point out is I've been talking a lot about gluconeogenesis, and it's next week's topic. Since it's so close to the exam, I'm going to bring it up once again. Gluconeogenesis is basically the opposite of glycolysis. Okay? So something I want to point out, being the opposite of glycolysis does not mean it's glycolysis in reverse. It's very similar to glycolysis in reverse, but if it were glycolysis in reverse, it would have to overcome this negative 35 kilojoules per mole free energy. It would have to, I mean, that's effectively, you'd have to break almost 2 ATP molecules. You'd have to hydrolyze them in order to make up for that. That's a lot of energy. So what can we do instead of having to do step 1 in reverse, instead of doing step 3 or step 10 in reverse? It's pretty simple. We just don't do that. So when you learn gluconeogenesis, step the opposite of 2, so once you get back down there, 9, 8, whatever the number ends up being, that's not going to be, step 2 is going to be the same. It's going to be catalyzed by phosphoglucoisomerase, and it's going to be fructose 6-phosphate to glucose 6-phosphate. Easy reaction. Step 1, step 3, and step 10 need different enzymes, or they need some kind of different situations because they're not going to happen in reverse. Okay? So coming back to these questions. Step 1, step 3, step 10. Okay? The next question says, what is the significance of phosphorylation of glucose? So like I've said before, this is a priming reaction. It helps set us up for future reactions. It also does a couple of other things for us, okay? The first is it introduces a negative charge. So whereas glucose is neutral, now it's negatively charged. Glucose being, I don't want to call it a large molecule since it's still only 6 carbons, but glucose being not one of the molecules that can fairly easily pass through the phospholipid bilayer. It can pass through. It sometimes needs a little bit of help, which is why we have a lot of glucose problems. Now it's negatively charged. No passive diffusion is going to allow it to get through the hydrophobic bilayer. So it's stuck where it is. So right now it's in the cytoplasm of our cell, assuming we're in an animal cell. If it's into the cytoplasm, it's now stuck in the cytoplasm. How does that help us? Now the rest of glycolysis is a lot more likely to happen because you're not having a ton of glucose going between the extracellular fluid and the cytoplasm. Okay? That rapid phosphorylation keeps that glucose concentration low and pushes more into the cytoplasm from the extracellular fluid. Okay? So the main reason is priming. Second reason is concentration in cytoplasm. All right. So which enzyme catalyzing the phosphorylation of glucose has a higher affinity for its substrate? A lot of words there. Basically, hexokinase and glucokinase, right? So the enzyme catalyzing reaction 1 is either hexokinase or in the liver it's glucokinase. So while the liver does need energy, primarily, if you've got glucose in the liver, it's because your glucose concentration in your body is too high. If your glucose concentration in your body is too high, your liver is going to start glycogenesis. It's going to start storing that glucose as glycogen. Okay? We don't want to do that when our concentration of glucose is okay, but not super high. So hexokinase has a higher affinity and thus a lower Km than glucokinase, because we want hexokinase to bind the glucose first in order to phosphorylate in the muscles and in the rest of the body, because we want to use that glucose as energy. When glucokinase gets a hold of glucose, it's storing it as glycogen. So we want a lower affinity because we only want that to happen at really high concentrations. Okay? So I'm going to repeat that because I think it is a little bit confusing. Glucokinase has a lower affinity and higher Km for glucose. Because glucokinase is in the liver and is primarily there in order to facilitate glycogenesis, or the formation of glycogen, we don't want that to happen unless our glucose concentration is like crazy high. So we get it. So it has a lower affinity, so that most of glucose is going to be used by hexokinases for glycolysis for energy, and it'll only significantly bind to glucokinase if there's a really high concentration and we do need to store some. Okay, so glucokinase stores glucose as glycogen, happens at high concentration. Okay. All right. So number 4, which step of glycolysis is the step in which a cell commits to metabolizing glucose? Right, I'm just going to go ahead and say it. Normally I would make a poll or something, but for the sake of time, I'm just going to go ahead and say it. Step 3. Okay, reaction of fructose 6-phosphate to fructose 1,6-bisphosphate. This is one of those reactions that at this point we're not going to go into glycogenesis. We're not going to go into any of these other various reactions. At this point, we're saying glycolysis needs to happen. We want to finish all 10 steps. Okay, that's step 3. What substrates are involved in phosphofructose regulation? And thinking back to enzyme regulation, what kinds of regulation are these? So phosphofructokinase, or for convenience, PFK, is one of the most regulated enzymes in our metabolic pathway of glucose. Okay, so one of the biggest reasons is, like we talked about earlier, it's got a really, really, really low free energy, so it's really spontaneous, that reaction. So because that reaction is spontaneous and early in the process, we want to make sure that we can stop, right? This is the step that commits the body to metabolizing glucose. So we want to make sure that we're only doing it when we need it. So to that end, ATP is one of the substrates involved. Why? Because at a high ATP, we've got a ton of energy. So do we need more of it? Do we need more ATP when we already have a ton of it? So high ATP, as you might guess, is an inhibitor. Okay. And more specifically, it affects the KM. So when we talked about in enzyme regulation K systems and V systems, we talked about the idea that a K system will change the affinity of an enzyme, but keep Vmax the same, whereas a V system will, will change velocity but keep the Km the same. So this increases Km of PFK, which decreases affinity. Okay. The next one, and we're going to get into the second part with labeling it all in a little bit. The next one is called citrate. So citrate, coming from the citric acid cycle, inhibits PFK as well. Okay. So let's think about this. Citrate inhibitors. So in order to get there, I have to go into the Tca cycle. In order to do that, I have to, first of all, have made pyruvate. Second of all, I have to be in aerobic conditions. So what this tells us is citrate will form only when we have a ton of pyruvate that we don't need right this second. Okay, so and I think I put the actual, I put the graph a little lower. So these are the fates of pyruvate that I want to talk about. I'm skipping ahead because I think it's really important to understand this talk. So pyruvate can either go into the Tca cycle and give us a ton more energy, which is awesome, or a Tca cycle and then electron transport chain, which is ETC, give us a ton more energy if we don't need it right that second. Under anaerobic conditions, on the other hand, so if I am exercising and I need energy right now, lactate is my answer. Okay? And then finally, in yeast, you can get ethanol rather than lactate. But I really want to focus on this idea that citrate is only formed when we have pyruvate that we don't need right this second. In other words, we have a lot of energy that we can get, so we don't need any more right now. So citrate in the future, or that's going to be formed in future reactions, is going to come back and inhibit PFK, right? So, and there are a few others. So, excuse me, in the liver, you have a fructose 2,6-bisphosphate. I'm going to be honest, I'm not 100% certain how much of that you need to know. I've seen some professors ask a lot about it. I've seen some professors barely mention it. And so I don't want to go into too much depth in case you don't need it. But just be aware that there's another regulation from fructose 2,6-bisphosphate, and that's a feed forward. Okay? So ATP in this reaction, I apologize, in reaction 3 is on paper the reactant right here. Okay, it isn't the most essential, or I should say, I'm sorry, since it's a reactant, we might think this is, hold on, when you have high ATP, ATP is a reactant, so we increase, or we decrease the delta G and make it more spontaneous. ATP is also an inhibitor. How does that make sense? So we have to remember that, yes, we're using ATP in glycolysis, but the end goal, what we're going to get out of it is a ton more ATP. So when we think of ATP, rather than as a reactant, as a future product, this is feedback inhibition. Okay, and so is citrate later down the line, because we're going to go through all these reactions to get to pyruvate. Then we're going to go through a couple more reactions to get to citrate. Citrate is also feedback inhibition. They both are. Okay. Which reaction in glycolysis is a redox reaction? So this is a question that I think a lot of people can get confused. It's also one of the simpler questions. Okay, so when we talk about redox, I should say at the beginning of this unit, during the chapter about metabolism, I think that was week 7 or week 8, we talked about catabolism and anabolism, one being an oxidation process, one being a reductive process. And the idea was we want a reductive process in order to get to NADH, NADPH, excuse me, and ATP, because those first two give us reducing power, okay? So, and the reason that I scrolled up to this reaction is because this is redox, right? We're going from NAD plus to NADH and 2 electrons. I should put the 2's here. But the point is, this reaction gives us more reducing power. Okay, so this is a redox reaction. And a lot of people will say, but the enzyme is called a dehydrogenase. A dehydrogenase is a redox, or I should say it's an oxidoreductase. It's a redox enzyme. So it's one of those oxidoreductases. I apologize for writing slow. There we go. Okay, so that's number 6. Reaction 6. Okay. What is the break-even point of glycolysis with respect to ATP, and is this reaction spontaneous? So we talked about this a little earlier, right? I drew this line right here and said at this point, we've made ATP to make up for all the ATP that we've used. So this reaction is kind of spontaneous when we look at this diagram again. Reaction 7 is almost 0. Yes, it's technically non-spontaneous, but it's so close to 0 that it's almost like neither. It's neutral, okay? So I'm just going to go ahead and say neutral. Which reaction is a condensation reaction? I already hinted at this earlier because I spent quite a while making sure that we were good with glycolysis. Reaction 9 is a condensation, okay? All right. So reaction 7 and 10 are both substrate level phosphorylation reactions that result in the formation of ATP. Why is reaction 10 so spontaneous and 7 is closer to neutral? So let's look back at reactions 10 and reaction 7, and we're also going to look at the energy diagram. So both reaction 7 and reaction 10 make ATP. So the term that I used in the question, substrate level phosphorylation, is a fairly common one. Okay. In fact, most of glycolysis is substrate level phosphorylations and then stuff to prep for phosphate for substrate level phosphorylations. Reaction 1, you're phosphorylating a substrate, substrate level phosphorylation. Reaction 3, same thing. Reaction 7 and 10, you're removing a phosphate from substrates, so it's a substrate level phosphorylation reaction. Okay. So reaction 7 uses magnesium, uses a kinase, gives us ATP. Reaction 10 uses magnesium, uses a kinase, gives us ATP. In terms of the enzyme, in terms of the actual reaction that's happening, very little is different. In fact, they're pretty much identical. And yet when we look, 7 is nothing, and 10 is impossible to get over. So why are they different? And this comes down to that enol that I circled right here. Because there's a more stable form of this enol, or I should say because there can be a more stable form. So this substrate is called Phosphoenol Pyruvate. Okay? There's a reason that it's not phosphoketopyruvate or anything like that. There's a reason that it's stuck as Phosphoenol Pyruvate. When we draw COO-, so this is, like we said, the enol form. If we were to try to switch to the keto form, we would get COO-, obviously still the same. Oh, that should be a negative sign. This should be positive. And this will be, also, oh no, is this positive? No, this one will also be positive, I believe. afraid I don't remember. I apologize. Oh, I think that's correct. In other words, it's a mess. No, this is negative. I apologize. Yes. Okay. So one of the things that we learned in organic chemistry is stability. Having a negative charge right here, not the most stable thing in the world. Having a negative charge right here, plus another positive charge, plus another negative charge, is very, very stable. This is really bad. And yet, the keto form generally is more stable than the enol form. So all we need to do is remove this phosphate group and then add a hydrogen down here, and we'll be really, really stable. Okay? In other words, the spontaneity of reaction 10 is partly driven by the breaking of that phosphate bond, that phosphate bond. But more than that, and really more than anything else, it's being driven by that keto-enol stability kind of debate. Okay? It's the conversion of the enol to the keto form is what really drives this reaction. So when we lose this phosphate group and that gets kicked off, the initial form that our pyruvate will be in is And so what's going to happen is we're going to have that equilibrium. Oh, and I apologize. This will take on a negative charge. Yes, a negative charge. Excuse me. We do that, and we add a hydrogen, and this gets so much more stable, and that is what drives Atp hydrolysis. And I'm also going to switch back to blue because I honestly didn't realize that I was writing in it until just now. Okay, so that is one of, I had a lovely diagram right here that would show. So we lose the ATP. We lose the phosphate in place of a hydrogen. Well, instead, this hydrogen can effectively move to here. The reality is it's going to dissociate, and another hydrogen will come in from here, from just HO or anything floating around. But for convenience, we'll say just that a hydrogen is released and a hydrogen binds. And what that does for us is it removes that keto form. It removes that enol form, that really unstable enol, and gives us a keto form. Okay? In other words, it gives, it makes phosphoenol pyruvate not have to be an enol anymore. And that's great for it, and that's what drives reaction 10. Okay? Question 10. What's involved in pyruvate kinase regulation? Okay, and once again, from our discussions on enzyme regulation, what does that have to do with anything? So, pyruvate kinase, once again, very spontaneous. Once again, cannot go backwards. So, gluconeogenesis uses a different enzyme. How are we going to stop pyruvate kinase when we're doing gluconeogenesis rather than glycolysis? That's the question we have to keep asking, and that's the question that makes all of this relevant. So, pyruvate kinase is activated by AMP. So ATP is adenosine triphosphate, AMP is adenosine monophosphate, okay? And it's activated by fructose 1,6-bisphosphate, okay? It's inhibited by ATP, if you guys couldn't guess. And aniline, however, I think aniline is not often asked about. So let's think about this. ATP is once again a product of future reactions pyruvate can take part in. Okay? this is feedback inhibition. There we go. Fructose 1,6-bisphosphate activates pyruvate kinase. So let's think about that with respect to all of glycolysis. So fructose 1,6-bisphosphate is, and I'm going to change color so that I'm trying to separate things out, is this thing over here. This goes in and activates this. Why? Okay. So this comes down to the idea that reaction 3 that forms fructose 1,6-bisphosphate is our step that commits to glycolysis. Okay. At that point, we know we're doing glycolysis through pyruvate, maybe through lactate, maybe we won't go to lactate, but at this point, we're going to pyruvate. So we need to tell it, hey, we're doing glycolysis, get ready. Okay. So this feed-forward activation, or this feed-forward regulation in general, helps to make sure that the rate of phase 1 of glycolysis and the rate of phase 2 of glycolysis are basically on the same page. Okay, so shifting gears down to here, this is feed-forward. I'll switch back to blue, because I forgot, feed-forward. Okay, what about AMP? AMP just kind of came out of nowhere, didn't it? So AMP, I guess, rather I should say AMP plus ATP can be used to make 2 ADP. It's a very common reaction that you're going to talk about in Biochem 2 if you take it. Basically, the point of this reaction is ADP can be more easily phosphorylated to give us more ATP, whereas AMP is just kind of a mess. It's not really helpful for us, and so we want to get it out of that form. So if you're going to have high AMP concentration, it means that if this is really, really high, it means that you cannot do this reaction because otherwise you would have. And that tells us that ATP is low. Okay, so when AMP is high, ATP is low. And I hope that makes sense, right? Because at the end of the day, it's adenosine in both of these. So the total amount of adenosine has to be fixed. So AXP equals AMP plus ADP plus ATP. So if this is fixed and you have a high amount of this and just some of this, we don't really need to worry about it, it means ATP is going to be lower. Okay? So the more AMP you have, the less ATP you have. That's why it's activating pyruvate kinase. Right? So I very briefly, I know that I mentioned this a little while earlier. I want to talk about this again in a broader conversation about rate. Okay? So if I have to give you kind of the overall goals of everything, the overall goal of glycolysis is to give us quick energy. Okay, glycolysis is a very fast series of reactions, excuse me. Okay. Once we finish glycolysis, we can do pyruvate conversion to acetyl-CoA, then the Tca cycle. This gives us a ton of NADH. This gives us a ton of ATP and 1 GTP. And then it gives us NADH that can go through into the electron transport chain, excuse me, for 2 reasons. Okay, we put NADH through there for 2 reasons. The first is because we want more energy, right? When you do NADH into the electron transport chain, you create a ton of ATP. You'll learn about that in the 4th unit of this class. The second reason, and the more important reason for the purposes of this unit, is we need to regenerate the NAD plus that we used, that we converted to NADH, so that we can make more glycolysis happen. Okay, so regenerate NAD plus from NADH. Okay, that's our overall goal of glycolysis. I apologize, of the electron transport chain. That's one of the overall goals, and for now, that's the one we're going to be dealing with. But this is a lot of reactions. I believe this is 8 reactions in the 8 reactions in Tca cycle, 7 to 8. And then the electron transport chain takes some time, right? So this is slow. It gives us a lot more energy, but it's really, really slow. Okay? On the other hand, this is one reaction. So if I'm running a race right now, I really, really, really need energy. So first of all, I'm most likely running out of oxygen because I've been exercising, and so I don't have as much available to my cells. Really important factor because the Tca cycle needs oxygen. The electron transport chain needs oxygen. However, another thing is if I'm running, I need the energy right now. I can't wait for a slow process like the one on the left here. I need something now. So lactic acid fermentation, or lactate generation, or lactate synthesis, whatever you call it, the primary goal of it is to give us more of this NAD+ that can go back into glycolysis to give us quick energy. Okay? That's why we eat carbs before a race, because we want quick energy from glycolysis. And under anaerobic conditions in yeast, rather than lactate, it's ethanol for a very similar reason. Okay? That reason, once again, we need quick energy, and we need energy that's available to us. In yeast, it's a little bit less, excuse me, it's a little bit less about the speed and more about the fact that they don't have access to oxygen, but that trend is still there. Okay? All right. So let's talk about these, excuse me. Let's talk about these energy differences. So first of all, these reactions are not balanced. It's just there to give us an example. So effectively, what we get out of the glucose to pyruvate step is pyruvate, obviously. We get NADH, we get 2 ATP, and then other stuff we don't really care about. The acid is nice, but it's not vitally important right now. On the other hand, with lactate, we get 2 ATP. Rather than pyruvate, we get ethanol, but we basically get some carbon thing we don't really care about. And we get, again, acid and water. Cool. So effectively, lactate gives us less, right? It's right there, NADH. We don't get any from lactate, we get it from pyruvate. Why is that important? Because we need lactate, obviously. I'm sorry, we don't need lactate. We need NADH as reducing power at some point, okay? Lactate gives us less energy. That's very clear. Lactate is not an ideal reaction. It is not perfect. It's also not healthy for us, right? It's lactic acid in our muscles. It doesn't feel good. But when we need that energy very quickly, we're willing to go through that lactic acid fermentation and lose that NADH because we really need that energy. Okay? So shifting gears from, I think, a bit more of a content-based portion to a bit more application portion, a bit more of an application portion. So a lot of the questions on your exam, I hope, are going to resemble some of the questions that I have from, I think, 13 through 20. So let's just go ahead and jump in and go through them. So insulin decreases the concentration of glucose in the blood. How might it do this? So this is a very application-heavy problem. I don't have very specific points written down because I think it's really important for us to go through it kind of mentally. So our ultimate goal is to decrease the concentration of glucose in the blood. Okay, so this means we have high glucose. So, I mean, I'll be the first to say it. Glycolysis could happen. So maybe insulin increases glycolysis. So maybe it does something to some of our cells that will, excuse me, that will make glycolysis more favorable somehow. It's not really likely because why would it do that if, or why wouldn't it have done that anyways, right? We should be using our glycolysis. We shouldn't need insulin to drive glycolysis if we've already got no energy. Okay, so maybe, but we'll see. Okay. So insulin could, rather than increase glycolysis, let's change that to increase cellular uptake. Okay. Why does this make sense? If glucose is in the blood, it's not in the cell. right? And we talked about, oops, I lost it, I apologize. I don't have the diagram in here. We talked about the idea that the phosphorylation of glucose inserts a negative charge, so it can't just diffuse back out of the cell. Well, if we're using passive diffusion to get glucose into the cells, that's fine. Why not use some energy to get glucose in there for sure? It's not energetically favorable because the point of having glucose is to make energy, so why would we use it? But if we have high glucose in the blood and it's not healthy, that could be a worthwhile way to do it. Okay. The second option is, rather than trying to push glycolysis to keep happening, why not favor lycogenesis? So the basic argument would be, if we have too much glucose and we don't need to burn it, or we don't need to exercise right away, so we're not going to be using it up very quickly, why not? Couldn't we just use that glucose and store it, right? So insulin can maybe somehow increase the synthesis of glycogen or the glycogenesis reactions, okay? And in general, it's going to increase a lot of our anabolic reactions, okay? So anabolism, thinking back, can anyone remember? Anabolism is the idea of making more complex molecules, right? So glucose is, in terms of complexity, it's one of those simple ones that we have catabolic processes to break down into even simpler stuff. Anabolism is building back up. Building back up takes energy. So since we don't need that energy to exercise right now, why not use the energy from glucose to rebuild my muscle? Why not reuse that energy from glucose to give my cells enough energy so that they can keep replicating through mitosis? Whatever the case may be. Sorry, I never finished this processes. Okay, insulin could be involved in any of these processes, and your slides, I believe, list these three and maybe one or two more. But these are kind of just the thought processes that we can take, because on an exam you won't have your slides available to you, obviously. Okay, which of the following enzymes is active first in glycolysis? So this is a memory question. I know that during this entire workshop I've been referring back to that diagram for convenience. But we do have to memorize the name of every reagent, every enzyme, and the order of the reactions. So for this one, I'm going to tell you guys, let's see. Okay, so the isomerase, that's after the cleavage, that's reaction 5. Phosphofructokinase, that's reaction 3. Phosphoglycerate mutase and phosphoglycerate kinase, we don't get a glycerate until phase 2. Right? We're dealing with glucose and fructose up until through phase 1. We get our glycerates in phase 2, okay? So the name of the enzyme and the name of the product can also help us out. So because of that, I know that these two are in phase 2, which means they're 6+. So phosphofructokinase is the first enzyme active in glycolysis of these choices, okay? How many molecules of ATP are produced by glycolysis? Okay, the answer that I think a lot of people are going to put is 2. The correct answer to this question is 4. Why? Okay, and this kind of hints at one of the questions, or one of the most common ways that students can be tricked. Okay, it's very common. I want to make sure that I emphasize that as much as I can. It is so common. It happens all the time. Okay. Phase 2, like let's split this into phases. Phase 1 and phase 2. Phase 1, we use 2 ATP. Phase 2, reaction 7 gives us 2 ATP. Reaction 10 gives us 2 ATP. And those are the the phosphoglycerate kinase and the pyruvate kinase reactions, respectively, for phase 2. Phase 1, it is hexokinase and phosphofructokinase. Sorry, I should have mentioned those. Well, we're getting a net of 2. But this question isn't asking us what is the net number of molecules produced. It's asking us how many are produced in general. We're producing 4. We're using 2 to produce those 4, but we're producing 4. So the important thing with this question, and the thing that a lot of people make mistakes on, is be mindful of exactly what it's asking you. This question can be asked in 6 different ways that will change the answer from either 2 to 4, about a dozen different times. Okay, that's really important. Okay. The mechanism of triose phosphate isomerase is very similar in function too. I put this question on here not because you need to know every single mechanism in detail, but because some professors do want you to know those mechanisms in detail. And so for the sake of making sure that I'm being thorough, I wanted to mention them so that you would know to check with your professor, what do I need to know? How much of it do I need? Okay, that's really important. Okay. I don't know if anyone remembers the answer to this one, so I'll wait a moment and see if anyone has an opinion. Okay, I'll give it away. It's an isomerase. We're dealing with isomerases. B. Okay. And this is also really good for us because let's think about it. The aldolase, this is reaction 4. It cleaves. It does the cleavage. There we go, since I wrote it that way. It cleaves our fructose 2,6-bisphosphate, or I'm sorry, fructose 1,6-bisphosphate into DHAP and G3P. Okay? This converts DHAP to G3P. So we definitely can't have cleavage happening here. Just adds a phosphate group. Phosphofructokinase just adds a phosphate group. Phosphoglucoisomerase changes something. Triose phosphate isomerase changes something. They're both isomerases. Okay. Which of the following enzymes catalyzes a reversible reaction in an equilibrium-controlled step of glycolysis? So there's a lot of words there. But, so which of the following enzymes catalyzes? Okay, let's just stop there. In other words, when we talk about the enzyme, we're really saying phosphofructokinase, reaction 3, the aldolase, this is reaction 4, reaction 10, and reaction 1. That's really what we're referring to. So which of those reactions is reversible and equilibrium controlled step, blah, blah, blah. Okay, so reversible is our key word here. I've been emphasizing a lot about the energy. Energy, 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 energy. It matters. It's very, very important because it plays a role in how reversible something is. Reactions 1, 3, and 10 are so spontaneous that they're not going to be easily reversible. Like I said, gluconeogenesis goes through a completely different mechanism for those reactions to avoid having to deal with how spontaneous the forward reactions are. That makes sense? This question, number 18, I got very similar ones. I actually included 2 very similar questions on this note because I missed this question on my exam. A very similar question, I should say. So I really wanted to make sure to emphasize being careful. Okay. So the oxidation of 1 mole of glucose, so we have 1 mole of glucose by anaerobic glycolysis. Okay. So anaerobic glycolysis is glucose pyruvate, and then pyruvate to lactate. Okay. In other words, it's the 11 steps, not the 10. Okay. So far we've been talking primarily about the first 10, and in those first 10, I know that the net, as it tells us, is plus 2 ATP, 2 NADH, and I guess plus 2 pyruvate if we want to think of it like that. This question does ask for that, pyruvate. So the 11th step says minus 2 pyruvate and plus 2 lactate, and minus 2 NADH, right? Because the point of this step is to go to reform our NAD plus in order to do more glycolysis. So pyruvate gone, NADH is gone. So the net of anaerobic glycolysis is ATP and lactate. In other words, it is 2 moles of ATP and 2 moles of lactate, letter A. Okay. Excuse me. Get rid of that. The oxidation of 1 mole of glucose by aerobic glycolysis yields a net. So once again, we're dealing with net. So we don't need to say or ATP plus minus 2 ATP. We don't need to deal with any of that. 1 mole of glucose, once again, this time it's aerobic. So now we're dealing with only 10 steps. So glycolysis to pyruvate. Okay, so in that case, we already know what happens. We just talked about that for the earlier problem. We get +2 pyruvate, obviously, because we're going to get plus 2, I was going to say +4, I'm going to say +2 AT and +2 NAD. So in this one, the answer is E. Okay. So so these two questions are very similar. In fact, the only difference is 2 letters, and yet they're completely different because of the 2 letters, which, to be honest, is part of the reason why I missed a similar question, because I wasn't reading anaerobic glycolysis. I didn't realize what that was referring to, so I missed it. So just be mindful of the questions that you're being asked, okay? And this also, I want to remind you guys, very similar to number 15. Is it saying how many molecules total or how many molecules net are produced? Okay. All right, and finally, number 20. What is the purpose of generating lactate from pyruvate? I did talk about this briefly, but I want to re-emphasize this because I think it's really important. It helps us to, I have lost my mouse, there it is, to regenerate NAD plus from NADH for more glycolysis. And this is only done under anaerobic conditions, because anaerobic conditions, first of all, we need aerobic for the electron transport chain. Second of all, because under anaerobic conditions, it means we're not getting a ton of oxygen. We need a ton of energy because we're most likely doing something athletic or something that requires that energy, which is why we're out of breath. So as a result, we need that glycolysis. Okay. So before we conclude for today, and I wanted to leave about 15 minutes, first of all, for questions. I don't know that there are any, which is, of course, absolutely great. But I also wanted to make sure, because your exam is next week, I believe it's next Thursday, but if it's next Tuesday, I sincerely apologize for miscounting that. I wanted to make sure to leave time for us to at least discuss again some of those topics, because I know that a lot of people have forgotten what all is on this exam, because it is a fairly diverse one. Okay. Before I do, I'm going to take a quick pause to make sure that I have a chance to answer questions, to make sure that you guys have a chance to ask those questions, etc. All right. Seeing none, I'm going to go ahead and just start. You need to know Chapter 15, Chapter 17, Chapter 7, and Chapter 18. So let's go through those in order. Chapter 15 is, excuse me, Chapter 15 is your chapter on enzyme regulation and reaction mechanisms. So week 8, I apologize, not week 7. So this one tells us a lot about allosteric regulation, feedback and feed forward, the idea of precursors, the idea of precursor molecules as another way of regulating enzymes, feedback inhibition again, and the idea of cooperativity. Cooperativity is a major topic that I think a lot of people get confused. The MWC and the KNF models, once again, really confusing topics that don't always make a ton of sense. Hemoglobin and myoglobin, and hemoglobin with respect to both of these models. Hemoglobin and myoglobin. A systems and V systems, like we talked about very briefly today. Phosphofructose kinase 1 with ATP follows the K system. ATP inhibiting its action, will increase the KM, decrease the affinity. Excuse me. V systems don't change KM at all. What they do is just change velocity. And then finally, metabolism. That's Chapter 7, if I'm not mistaken. Yes. Oh no, I apologize. Metabolism in Chapter 17. Excuse me. So Chapter 17, the basic difference between catabolism and anabolism. These definitions that nobody wants to learn about phototroph, autotroph, chemotroph, and then the 2 specific ones within chemotroph. and this idea of metabolic pathways being regulated because they're using a lot of similar enzymes. The idea that they're using a lot of similar enzymes tying into the fact that that means that they have relatively low free energies, that corresponding to making it easy to do reverse reactions, which also means ones that aren't like that have a very high or have to be done differently by those reverse reactions, or by those by the reverse processes. So this diagram is a great example of that. The catabolic process, for example, of glycolysis. Reactions 1, 3, and 10 are these ones in this box. These would be the reactions of glycolysis because the free energy of one of them is really, really high relative to the other one. And so it's very easy to, or I should say exactly like it says here, these are very spontaneous in one direction. These can go forward or reverse because the delta G is near 0. Okay. Compartmentalization and metabolism. Relatively important topic, but not the most important in my opinion. Okay, and then I believe chapter 7. Yes, chapter 7, Introduction to Carbohydrates. So the idea of L and D isomers, and the idea that they're not just isomers at that last carbon, they're isomers, they're enantiomers, so they're complete mirror images of each other. Alpha and beta forms of a sugar, how that corresponds to alpha and beta glycosidic bonds. A little bit more about things like glucose and galactose being different, or I should say a little bit more about glycosidic bonds. And to that end, once again, I want to reiterate, I believe I said this last week, make sure to ask your professor which carbohydrates you need to have the structure memorized for, if any, which monosaccharides, I should say. And then we shifted into polysaccharides, so things like amylose, amylopectin, starch, and chitin were talked about in your book. I'm sorry, in your book and your slides. I'm not sure how much you need to know for them. Gram-positive and gram-negative bacteria, once again, mentioned. Not sure how relevant they are for your specific course. And then we got into glycolysis. Glycolysis, really everything is fair game because this is one of the most important reactions. So they want to know a ton about regulation of glycolysis. They want to make sure that you know everything about, oh, sorry, I never actually finished writing this, reaction 9. They want to make sure that you know everything about basically the enzymes, about the favorability. One of what I personally believe to be the easiest questions for them to ask is this idea of, sorry, I skipped it, hexokinase versus glucokinase. It's a really important topic that really helped you segue well into gluconeogenesis, which we'll be talking about next week. And it's a really interesting and important topic for enzyme regulation as a whole. Okay, so it really does help tie in all of these units together. Oh, these kinds of topics are pretty big. So a fairly common question, and this is more an exam 4 topic, just in case I thought to mention it here. You may be asked something like, if I introduce, what's that? I'm afraid I'm blanking on the name. 3-phosphoglycerate, for example. How much ATP will I get out? How much will I use, etc. Things like that can be asked. Again, they're more common in Unit 4. They're fair game because it is something that you should be able to answer pretty easily. And then just once again, reiterating, having all of the enzymes, having all of the substrates and products memorized for all of them. Knowing that magnesium is a cofactor, it's not a common question, but I have seen it before. And then kind of understanding the purpose behind each of the reactions. So why would we go through the Tca cycle? Why would we go through lactate? Why would we go through a reaction that takes up energy? Why are some reactions more or less energetically favorable than others, et cetera, et cetera. Okay. All of these topics are completely fair game for your exam. All of them are, in my opinion, also incredibly important for your biochem education as a whole. So next week, I'll have a pretty decent lecture, or not lecture, review of gluconeogenesis, just to make sure we talk enough about it for you guys to see the differences between it and glycolysis and to see the purpose behind it, because that's something that I really didn't understand for the longest time. And then once we finish that, I'm going to have a couple of short questions just over the past few weeks to make sure that we can review it for your exam so that you guys are ready for Thursday. Okay. If there's nothing else, thank you all for coming, thank you all for watching, and good luck on your exams.